other. Please do not use any inappropriate or offensive language or any content in that way. That is not to be tolerated. Please do not share your personal details. That includes your mobile numbers, your emails, your addresses, your social media contact, and that's with your peers and the mentors. Please only use the channels that are designated for you to use. So I think that's going to be Slack and things like Zoom. Do not contact any of the mentors outside of those channels. Try and keep the chats on topic, I guess, to keep it from distracting people, and do not record the meetings in any way. We will do that and distribute. You don't need to. And for just because I know some people might watch this afterwards, to go back to what I was saying, so that's our code of conduct. And just to introduce myself, I am the designated safeguard leave shard. So if you do have any concerns, please do contact me. You can also contact Vlad if you want to talk about anything. So we're here to help. Has anyone got any questions? Okay, well, otherwise, do get in contact if you need anything. Otherwise, good luck with the session, and I will be in touch. I'll probably be dropping into some of your sessions, so you will see me again just to see how things are running. Okay, thanks very much. Bye.
Okay, thank you. David, you're now the host, and yes, to you.
Okay, good evening, everybody. Vlad, do you know how many webinars there's going to be on the partial derivative sheet?
The deadline, the deadline for submissions is this Sunday. So this is the one and only. The one and only.
Okay, so I'll try and cover everything, including some of the vector calculus. Okay, so I'm going to start with a little bit about inverses. So this is where the sheet started. So show that f of x is, which is defined to be sinh x over cos x, is a one-to-one function, and establish its range. What would we do in order to establish that a function is one-to-one? Under what conditions will a function be one? And what condition? Verify that it's odd. No, not all odd functions are one-to-one, because a function could be odd and look like that, and it's not one-to-one. Show that it's, yes, show that it's strictly monotone, either strictly increasing or strictly decreasing. And what would be the easiest way to show that it's strictly monotone? Well, we know we've got a nice condition to show that something is increasing. We can differentiate it. So we could go f dash x. This is a quotient. So u is equal to sinh x, v is equal to cos x, and we need to find u dash and v dash. Now, I'm not certain how, just in case anyone is not familiar with these hyperbolic trig functions, sinh x as a definition is e to the x minus e to the minus x over 2, and cos x is e to the x plus e to the minus x over 2. And so if we differentiate sinh x, the e to the x remains as e to the x. The negative e to the negative x, we pick up a second negative from the chain rule, and we get that sinh x differentiates to make cos x. So u dash x is cos x. If we differentiate cos x, the e to the x differentiates to e to the x, the e to the minus x differentiates to e to the minus x, and we get that cos x differentiates to sinh x. We now do the quotient rule, so we do vu dash minus uv dash, so we get cos squared x minus sinh squared x all over cosh squared x. Okay, now again, if you're familiar with hyperbolic trig functions, this numerator you'll be able to process straight away, and it will just be a known identity. If you're not, we can always work with the exponential forms. So cosh x all squared is just e to the x plus e to the minus x over 2 all squared, which is e to the 2x plus 2 plus e to the minus 2x over 4. The 2 is just the middle term of the square. The sinh squared x, we've just got a minus sign. So we get a very similar expression, except we get a minus 2 in the middle. And when we subtract, we equal 1. So we get that f dash x is 1 over cosh squared x. Okay, and that is strictly greater than 0. So f dash x is greater than 0, implies fx is a strictly increasing function. And therefore 1-to-1. Next part, establish its range. What would we do here? Well, we've got a strictly increasing function. We also happen to know it's odd. So it's not its maximum, but its upper bound is going to be the limit as x goes to plus infinity. Its lower bound is going to be as x goes to negative infinity. So we're going to calculate these limits. The limit as x goes to infinity of f of x. I'm going to use the exponential forms. So sinh x is e to the x over e to the minus x. Cosh x is e to the x plus e to the minus x. So that's e to the 2x minus 1 over e to the 2x plus 1, which as x goes to infinity just converges to 1. Because we can write it as 1 minus e to the minus 2x over 1 plus e to the minus 2x, and these two terms both go to 0. And then the limit as x goes to minus infinity, very similar calculation, goes to -1. So this is or we could just argue that it's an odd function. So we've got horizontal asymptotes at -1 and 1. We never attain those asymptotes, so the range is -1, 1. Okay, that little interlude has got little to do with the sheet because it's just looking at inverse functions. Let's now look at finding an expression for the derivative of the inverse function. And we're going to do this two ways. We're firstly going to do this without finding an expression for g of x. So we've got f inverse x is equal to y. Can anyone give a suggestion of how I could find, so this is g of x. Can anyone think of a way of, so I've got g of x equals y. Can anyone think of a way of rearranging this into a form that I can differentiate without needing to go through the rigmarole of actually finding the expression for the inverse? But we might have seen this with differentiating a logarithm, differentiating inverse trig functions, we can differentiate implicitly. So we don't understand F inverse, but we do understand how to differentiate F. So I can write the implicit relationship x equals f of y. And now I can differentiate with respect to x. So if I differentiate with respect to x, the left-hand side becomes 1. What is the derivative of f of y with respect to x? Any suggestions in the chat? Yeah, excellent. So a good way of thinking about this is the chain rule. We know how to differentiate f of y with respect to y. But to make the chain rule work, we now multiply by dy by dx. Naively, we can conceive of the dy's cancelling. Now, d by dy fy, we can recycle our expression for the derivative. That is 1 over cos squared y. And then we multiply by dy by dx. So we get dy by dx is equal to, how do we want to write it? We can write it as cos squared y if we want. What is the issue with this expression for the derivative? So we've got y is equal to g of x, and we've got dy by dx is equal to cos squared y. What is unsatisfying about this derivative? I'll confirm I've not made a mistake, but there's something unsatisfying about the answer. Yeah, okay, we've got a derivative in terms of y when the function is in terms of x. Now, when I wrote the sheet, I really wanted to make clear that in very many circumstances, we're not going to end up with a neat expression where we can get things back in terms of x. What we would need to do here is try and find some expression for cos squared y back in terms of x. And the trick is to use this relationship that we've proved previously, that cos squared y minus sinh squared y is equal to 1. So if we divide by cos squared y, we get 1 minus tang squared y, or sinh squared y over cos squared y. over cosh squared y. And so we get cosh squared y. Now, can anybody come up with a suggestion of why this expression is convenient for our purposes in terms of the question? So what we've got here is we've got dy by dx is equal to 1 over 1 minus, I'll write it as sinh y over cosh y all squared. Where have we seen this sinh y over cosh y? Well, that is exactly f of y. But that is if you think back to what we've got, we know that y is f inverse of x. So if we make an expression which is f of y, that is exactly an expression for x. So here we've got dy by dx is 1 over 1 minus x squared. Okay, so what we were looking for is we were trying to get this expression in terms of x. And we should remind ourselves in the context of this question that x is tan y. Just a sanity check. What features of this derivative look right? Why does this derivative have the right sort of properties? Well, let's think about my expression, my curve for y equals tan y. The inverse function will be defined on -1, 1. And it will just be this function reflected in the line y equals x. So the inverse function will have vertical asymptotes at -1 and 1, which is the same property as this derivative here. Okay. So the derivative looks right, and indeed the derivative is right. Does anybody have any questions about that part before I move on? If you're happy, just put a thumbs up into the chat. Okay, lots of thumbs up. Just for the sake of completeness, I want to have a look at doing this question in a more sort of less high-tech way of actually finding the inverse function and seeing if we get the same result. So we have got y is equal to f inverse x. So x is equal to f of y. And f of y we know is e of y minus e of minus y over 2 over e of y plus e of y over 2, which is e of y minus e of minus y over e of y plus e of minus y, which I can write as e of 2y minus 1 over e of 2y plus 1. Suggestions. How do I make y the subject? So logs eventually, yeah, form a quadratic, okay? So I'm going to multiply both sides by the denominator, so I get x times e of 2y plus x is equal to e of 2y minus 1, which I can write as x minus 1 e of, actually I'll write it as x plus 1 is equal to e of 2y 1 minus x. So e of 2y is equal to x plus 1 over 1 minus x. So 2y is the natural log of x plus 1 over 1 minus x. And so y is 1/2 log of x plus 1 over 1 minus x. What would be the easiest way to differentiate this function? We could differentiate using the quotient rule, but there's a slightly simpler way. That if we actually write the two logs as a subtraction, becomes a little bit easier to differentiate. So we get y dash is 1/2 over x plus 1 when we differentiate the log. When we differentiate the log of 1 minus x, we pick up an extra minus. And then when we add the two fractions, we get 1 over 1 minus x squared. So the result is the same. So yeah, again, maths has done the job. Maths has worked. Just as a vote, who prefers this method of differentiating implicitly? And who prefers this method of explicitly finding the inverse? I'd just be interested to see. Not sure what my preference is, but just put in the chat a vote for implicit or explicit, and we will take a vote. Oh, we've got 1 vote for explicit. Oh, we've got a tie. Oh no, we've got 3 votes for explicit, 4 votes for explicit. Oh, it's close. Yeah. I wonder what I prefer. Explicit. I think if I can do it explicitly, then I prefer explicit. I think where I feel unsatisfied is those many occasions when you get a relationship for the inverse function, but you don't get the inverse function in terms of x. Okay, let's look at some parametric differentiation. I'm going to do question number 2 together. So it says the points P, AP squared 2AP, Q, AQ squared 2AQ, both lie on the parabola y squared equals 4AX. And they're such that the angle QOP equals 90 degrees. This is a bit more, this is slightly, actually, I'm not going to do 2, I'm going to do 1 because 1 doesn't involve any differentiation. So let's do question number 1. Show the point T, AT squared 2AT lies on the parabola y squared equals 4AT. Find the equation of the normal to the parabola at the point T. So how can I differentiate this parabola y squared equals 4AX? Suggestions in the chat. We'll take a vote. But I think there's at least 2 ways of doing it. Okay, so what we can see is that we could either regard this as an implicit function. It's an implicit function because y is a relation of x, or we could use the coordinates that are given for x and y as a parametric form. So we could say that the general x coordinate is a, and I'll call it p squared, so I don't use the same parameter twice, and y is equal to 2ap. So if I was to do it parametrically, I could say dy by dp is 2a. I could say dx by dp is 2ap. And if I take the quotient, dy by dx is 1 over p. Alternatively, I could differentiate implicitly, so I could say 2y dy by dx is equal to 4a, so dy by dx is equal to 2a over y. Either way, when I substitute in my y, either my y value of 2at, I get dy by dx equals 1 over t. Over here, if I substitute in the value of the parameter as at t, dy by dx is equal to 1 over t. So this is implicit, and this is parametric. It then asks to find the normal to the parabola at the point t. So the gradient of the tangent is 1 over t. The gradient of the normal will therefore be negative t. So we can fit the normal in the normal way. And so we get y is equal to 2at minus tx plus at cubed. How are we going to find where this line hits the curve y squared equals 4ax? There's what would be the naive way would be to square the expression for y. And that would end up being horrible. But a much better way is to use the parametric form. And so the parametric form would be to use y. Whoops. I think I might do, yeah. Okay, I'll send her. Sorry, I just need to do something very quickly. I'm just going to give people 5 minutes to finish this question. I will be back. And if you finish this question, have a look at the one below it. Sorry, I'll just be 3 more minutes. Sorry. Apologies about that, minor crisis. Where were we? So we were trying to find the intersection of this line and this curve. Without any doubt, the best thing to use is the parametric form of the curve. So we know that a point that lies on the curve y squared equals 4ax will be of the form ap squared to ap. And all I've done is I've taken the same form as the point t, but with a different parameter. So if I substitute that into this normal equation, my y becomes 2ap. My x becomes ap squared. And I've got at cubed. Cancel. And so I get tp squared plus 2p minus 2t minus t cubed is equal to 0. So I've got a quadratic in P. Does anyone want to give me a very sensible way of solving this quadratic? So there's lots of unsensible ways of solving this quadratic. We could use the quadratic formula. But does this quadratic have any... Right, we could... So someone has suggested dividing by p minus t. Now, why is p minus t an obvious factor of this quadratic? Well, what we are finding, and I think if I was doing this question in your shoes, I would have drawn the diagram at the beginning. We've got a quadratic. We've got a parabola, sorry, we've got a point T on the parabola. And we are looking at where the normal hits the curve again. So this line is the normal. And we're trying to find the parameters of the points where the normal hits the line. But there's 2 points of intersection, but one of them is very obvious. One point of intersection is T. So one possible value of P is T, and now we just need to obtain the other bracket. So to get a TP squared, we get a TP. To get a minus 2t minus t cubed, we need a plus 2 and a plus t squared. And if I do that, I get a 2p, yes, and that works out. Okay, so one value of p, which is very boring, is p equals t. The other value of p is negative 2 plus t squared over t. How do I then go and find the coordinates of where the points hit the curve again? Well, I know that this parameter can go back into the parametric form for the curve. So I get a, and then 2 plus t squared over t all squared. And then I get minus 2a, 2 plus t squared over t as the coordinates of my point. Okay, so this question is quite nice. It's a little bit of sort of differential geometry. It shows that there's can be a choice in whether to use an implicit function or parametric differentiation, so they shouldn't be seen as either or. Okay, and you should look for the one which is most convenient. I think here there's something of a tie, but at this point later on, we were much better off using the parametric form. Any questions about that question? Or if people are happy, just put a thumbs up in the chat and I will move on. Okay, lots and lots and lots of thumbs up. Excellent. Right, I've written some handwritten questions here. And I remember very clearly being your guys' sort of age and doing a question like this for the first time. I remember the first time I hit a question where I was asked to find the length of a curve. And I remember feeling, I don't quite know the adjective. I just remember suddenly thinking, oh my word, I've done all this calculus and there's this big hole of, I found areas of curves, but never lengths. And it sort of struck me, why did I never think of doing that? Now, I don't know if people have seen this, but if people haven't seen this, I think this is a good opportunity to sort of think about people's like intuition. What would I do in order to find the length of a curve? Now, I think it's relatively difficult to explain the full method, but does anyone want to just put any ideas into the chat? And this is the simplest curve we're ever likely to meet. This is the curve. It's just our favorite y equals x squared curve. Any initial ideas of how you would even approach this using techniques, skills that you know? There's something coming into the chat. You could take lots of little small arc lengths. Okay, so let's think about this idea. So we take lots of little points on the curve. Okay, so this is the classic integration idea. So let's just zoom in with a big magnifying glass on one. So we've got a smooth curve. We've got 2 points on the curve. And let's call this horizontal distance delta x. This vertical distance delta y. So to a good approximation, what would be a good approximation for the length of that arc? So for this arc length, let's call it delta S. Someone said delta x equals delta y. Well, it doesn't, does it? What does how's delta y related to a good approximation? What does delta y equal? Well, we know that delta y over delta x to a good approximation is dy over dx, which is, for this curve, 2x. So this height is 2x delta x. Okay, because obviously delta y, the curve gets steeper, so delta y becomes, as x becomes larger, delta y becomes larger. So the approximation to the arc length would be this straight line distance here. And we might come back to this approximation for delta y later. But what expression can I write down for that pink, for this pink line, the length of this pink line here? Pythagoras, excellent. So delta x is the delta s, which is the increasing length, is a little bit like delta x all squared plus delta y all squared. Okay. Now, as it stands, this isn't like any mathematical, you know, like object. But I'm going to do something. I'm going to do a variety of things. But the first thing I'm going to do, I'm going to divide by delta t. I'm going to divide by delta t because you guys are all physicists. Okay. Now, if I divide by delta t, I get delta s over delta t is equal to the square root of delta x squared plus delta y squared over delta t. And then I take the delta t inside the square root, and I get delta x over delta t all squared plus delta y over delta t all squared. And now I'm going to let delta t go to 0, and I'm going to say that the rate of change of the length of the curve is equal to the square root of delta x over delta t all squared, sorry, dy by dt all squared plus dx by dt all squared. Physicists, help me. I'm just a humble mathematician. What does a physicist say is going on here? So the rate of change of length of curve is equal to this expression on the right. Not acceleration. So there's a not quite velocity, right? Okay, not quite velocity. Okay, what is the, if x and y are changing over time, then the velocity vector, so if the position is x, y, the velocity vector is dx by dt, dy by dt. So if that's the velocity, what expression is this square root? The speed, excellent. Someone in the chat, Noah, put speed. Yeah. If we know the velocity is, I'll call it x dot over y, x dot across and y dot across as the two components. If we know the components of the velocity, we can use Pythagoras's theorem to find the speed. But what is speed? Now, speed, from a physicist's point of view, is the rate of change of distance traveled. But in order to find the length of the curve, that's exactly what we want to do, because we don't want to find the overall displacement. We don't want to find the point that we've moved from and to. But what we actually want to do is find the distance that we've traveled. So this expression on the left, ds by dt, which I rather clunkily call length of the curve, the rate of change of length of the curve is what from the velocity. Okay, so what we've got here is a meaningful expression that ds by dt is dx by dt all squared plus dy by dt all squared. That, I did that as a little motivation that I could divide by d. If I divide by dt, I get the right sort of expression. So what I could divide by instead is I could divide by dx. So I get ds by dx is equal to the square root of 1 plus dy by dx all squared. So I get ds, if I let dx, delta x go to 0, I get ds by dx is equal to the square root of 1 plus dy by dx all squared. But dy by dx, we know for the curve s squared is root 1, it is 2x, so we get 1 plus 4x squared. So we now know the derivative of the length of the curve with respect to x. What do I actually do to find the length of the curve? I'm expecting lots coming into the chat. So I know I've got an expression for ds by dx. So what do I do to undo that? Well, I've got differentiation. So yeah, people are right, I integrate. So the length of the curve of my parabola between 0 and 1 is the square root of 1 plus 4x squared dx. Okay, and now this is, if I mentioned at the beginning that I was shocked that you tend to do lengths of curves relatively late. The reason you tend to do lengths of curves relatively late is the integrals often come out to be difficult. I won't do, this isn't a sheet on integration, so I won't do this integral. But does anyone have any suggestions of what might be a good substitution to use? And I'll give you a clue, something we saw earlier might be useful. Ah, yeah, that's good. So, yeah, so some people are saying u equals 1 plus 4x squared. You can try that, but that doesn't get rid of the square root. What we've got here is 1 plus, and I'll show you my way of thinking of it. We're trying to integrate 1 plus 2x all squared. Now, wouldn't it be lovely if 1 plus 2x squared was something else squared? Now, for that to be true, we want 1 to be something squared minus something else squared. Now, do I know any identities like that? Well, I saw one earlier. I saw that cosh squared x minus sinh squared x is equal to 1. So if 2x, sorry, I'll put a different letter, was, if my star here, my 2x, was sinh squared u, I would be in a much better position. So my recommended substitution here would be 2x is sinh u. And so in other words, x equals sinh u over 2. Because then my square root would just be the square root of cosh squared u, which would be cosh. I'd pick up something from the derivative, but I'd end up with a doable integral. Yeah, so people have put sinh u over 2 into the chat. Well done, Javier. Okay. Any questions about that example, about lengths of curve? Put a thumbs up if you're happy. Just out of interest, has anyone done this before? Has anyone used integration to find the length of a curve before? No, good. Nah, good. Someone's done it recently. Lots of no's. So that's good. That makes me feel happy that you've learned something. And if there's time, we might do some more. We might do some more geometry of this type of breaking things up later. I'm not sure there will be time. Okay. Oh, yeah, this is something which is not often done. The second, so we've got a parametric curve, and we're asked to find the second derivative. So I think everybody knows the first derivative. dy by dx is y dot t over x dot t. Explain the method you'd use in the chat if you were going to find an expression for the second derivative. What's the challenge? So we know that d2y dx squared, we would need to differentiate with respect to x. So what is the challenge of differentiating this fraction with respect to x? Well, everything inside the bracket has got a bit of a tight mismatch. It's a function of t. So what we would want to do on the right, we'd be much happier if we were differentiating with respect to t. But we can't just differentiate with respect to t willy-nilly. We'd need to invoke the chain rule and have a dt dx. But that is the same as dividing by dx by dt. Start. And then how do we differentiate this fraction? Well, the clue is that it's a fraction. So we would do the denominator, which is x dot t, multiplied by the derivative of the numerator, which is, so we get y double dot t. Then the other way round, x double dot t, and then over u squared, so we get x dot t squared, and then we've got another x dot, so it's over x dot t cubed. Okay. So what condition is satisfied if x dot t y double dot t is equal to y dot t x double dot t? So this corresponds to a point where the second derivative is 0, and we say that a point is where the second derivative is 0 is a point of inflection. And I'll let you physicists ponder what that tells me about velocity and accelerations and stuff like that. Right. So what I've done so far is questions on inverse functions, implicit and parametric functions. So like the first bit of the sheet. I hope you were excited and felt really grown up by the second half of the sheet that started to look at partial derivatives. Okay. I think it's worth saying at this point, don't be at all put off if you don't understand everything on that second half of the sheet the first time that you do it. It takes quite a lot of time to get used to the concepts, the notation, and so forth. I remember, again, being roughly your age, of starting to use symbols like this and just feeling like I was suddenly doing like magic, and people would look over my shoulder in the sort of university library and you'd be drawing all these symbols and you just feel really sort of proud and so forth. Let's have a look at this example. So firstly, I say phi x, y, z is a scalar field. What do people do people want to put in the chat what they understand, if anything, by a scalar field? Or if that's a bit difficult to explain it in sentences, can somebody give me an example of a scalar field? Good. So someone's put wonderful sentences. Every point in a region has a scalar value. Yeah. So you've got space, and at each point in space, there's some numerical quantity. So not a vector quantity, but some numerical quantity associated with that point. And the same person has given the example of temperature. Brilliant. Yeah. Like the elevation above sea level of a map. Yeah, absolutely. That would be a sort of 2-dimensional example, but I think the 2-dimensional example is conceptually no more, is not that different to the 3-dimensional example. I think with vector calculus, broadly speaking, the big leap is from 1 to 2 dimensions, and then there's not such a big leap between 2 and 3 dimensions. There are some respects. Okay. So the first symbol here, this upside down delta, is just something which I'm introducing in this question. It's a standard piece of notation that we'll meet later, and it's called the gradient of phi. And what this does is at every single point, your del operator or nabla, very good, Yusuf. So what this is defining is at each point in space, it's defining a vector. So this would be a vector field. Okay, now it says a particle has position vector RT, and UT is equal to phi RT. I really like the high elevation in a map example. Okay, and so I've got one of these little sport watches. So imagine I go on a run, okay, and my Garmin, sorry if I don't mean to do product placement, just tells me my elevation at time t. So this is phi, this is t, and one possible thing is elevation. Okay. Oops, this shouldn't be a vector. Okay, so my position vector at time t is RT, and my elevation is phi RT. And then it says, find an expression for U dash t. Okay, so let's try and think between at some new position t plus delta t. Sorry, this is my position. Let's consider my position. At time t, I was at position RT. Physicists amongst you, where will I be roughly delta t seconds later? So here I am running around. Here I am at time t. Here I am at some little time later. What physical quantity, or quantity from physics, tells me how my velocity has changed over that short time interval? So between t and delta t, I haven't really changed direction very much. So I'm running in the direction of my velocity. And so my displacement is going to be my velocity vector times delta t. If I rearrange this, this is just my displacement, or change in displacement, and this is my change in time. Okay, and now my new position is RT plus my velocity, which is dx by dt in the x direction dt in the y direction. Elevation. So what I want to do now is I want to find u of r t plus delta t. And so that is u of RT, so my previous position. And then my displacement is a vector. Okay. Let's consider the ground. And this is the really important part of the sheet. Okay, so this thing here is my horizontal displacement. And this thing here is my vertical displacement. Or my, let's call it east and north. And then I'm going to use vertical for up. So this is my x direction and my y direction. Now let's consider the lie of the land, okay? So I'm running, and I'm running along some sort of rough terrain. If I was just to run east, okay, what mathematical expression tells me the gradient of the land in the eastward direction? So this, so u of, we've got the x direction, we've got the y direction, the elevation is u x y. If we fix a point and we just run eastward, we've just got a one-dimensional curve. And we just do all the stuff that we've always done in one dimension, where we know that the gradient is the derivative. But because we're keeping y fixed, the gradient at a point, so let's imagine I'm here, the gradient is not the derivative, but the derivative, the partial derivative when x changes and y remains constant. Now, if I run, so as I'm running, I'm starting at this point. If I run a little bit east, okay, I go up this, the amount that I've gone up vertically is the gradient of this tangent. And the gradient of this tangent is, sorry, du by dx, multiplied by my displacement. So what this, if I just run horizontally, my horizontal displacement is dx by dt delta t, and my vertical displacement is that multiplied by the way the elevation is changing if I run eastward, and that is the partial derivative with respect to x. And so that's the gradient, and then the rise is dx by dt delta t. So this component of my velocity, the eastward component of my velocity, changes my vertical displacement by du by dx times dx by dt times delta t. Okay, you could imagine me running in a bit of a funny way. So I'm running, and what I do is I run a little bit east. So I do this part of the velocity, and that sends me up. But then I do my little shuffle north, and when I go north, I'm following the land in this direction, just north, and I have a very similar position, but in the northward direction, my displacement is determined by the northward component of my speed, so dy by dt, and the northward gradient. So then to get my elevation is now du by dy. So this northward displacement sends me up by du by dy, which is the gradient, multiplied by that displacement. Can I just get at this point, thumbs up if people understand what I'm saying? Kind of some sort of mixed emoji if they're completely confused, and an upset face if they're just completely baffled. So this term here is the gain in elevation due to my eastward motion. And then I get a similar term due to the gain in elevation in my northward motion. Oh, we've got lots of thumbs up. That's brilliant. Okay, so overall, The gain in my elevation is these two components. So delta U, so the difference between this and this, is du by dx times dx by dt plus du by dy times dy by dt, all multiplied by dt. But then if I do it in 3 dimensions, I've also got, I can put in my vertical motion. And then if I divide by dt, I get du by dt is equal to du dx dx dt plus du dy dy by dt and du dz dz by dt. Now, let's go back to this funny operator that I mentioned earlier. These 3 partial derivatives are the I, j, and k component. So this is the I component, or the x, the first component of del u. This is the j component of del u, and this is the k component of del u. So what does this expression here look like? Which mathematical thing? Notice that dx dt, dy by dt, and dz by dt, they're the 3 components of which vector? They are the components of the velocity. So which mathematical thing do you get by multiplying the I components of 2 vectors together, the j components of 2 vectors together, and the z components of 2 vectors together and adding them? So we get du by dt. That is just the I'm wondering if u should be phi. Yeah, u is, sorry, by u I mean phi. Yeah, sorry. Okay, so I've got du by dt is d phi dotted with the velocity. Okay, so if I'm running, if I want to get the rate at which my elevation is changing, I look at the gradient vector dotted with phi. Right, let n hat be a unit vector. What is the geometric significance of grad phi dot n? So let's make my velocity just n. So n hat t. Sorry, my position just, yeah, let's make my velocity n hat t. So the rate of change of elevation is just grad phi dot n. So what does this mean? Okay. So let's do it in, let's imagine we're doing it in 2 dimensions. So we're doing this example of the elevation of land. We've got at each point a vector, which I'm going to call grad phi. And if I run in a direction, let's call it n hat, the rate at which the elevation is going up is grad phi dotted with n. So what happens if n hat is just in the same direction as grad phi? Well, what we get there is that it's just the length of the two vectors multiplied by the cosine of the angle between them. The angle between them is 0, so that's just 1. So we get grad phi. But as n stops being parallel with grad phi, we get grad phi multiplied by the cosine of the angle between them. So the rate at which elevation goes up decreases as that angle increases. So if I am running in the direction of grad phi, I am going up, the rate of change of my elevation is going up as much as possible. So if you were hill walking, if you're running in a hill, when would you be walking in the direction of grad phi? You'd be walking in the direction of grad phi if you were going up the hill as steeply as possible. So whichever way, you look at the hill around you, there's one direction which is steepest up, the steepest ascent. If you go in that direction, you're following grad phi. What's the magnitude of grad phi? Well, it's the steepness of the slope in that direction. Okay, so let's take, so you're climbing a mountain. One choice is to just go straight up the mountain. The other option is just to contour round. Now, if you contour round, what direction are you walking in? So when is this expression? When is this expression for the rate of change of elevation 0? So when is the dot product of two vectors 0? When they're perpendicular. So if you imagine a hillside, if you walk straight up the hill, your elevation will increase. So let's imagine you're walking on a hill, and if you go north, that's taking you towards the top of the summit, or no, I'll do it east. But if you walk north, you're just going to contour around the side of the hill. Okay, so grad phi dot n gives you the directional derivative. Now there's two special cases. If I dot grad phi with just the unit vector I just get the first component of grad phi, which is d phi by dx. And that's just that special case that the partial derivative is the gradient that you get if you walk along the hillside eastward. Okay, so what we call grad phi dot n is the directional derivative. In the direction of n. Okay, let's look at the question. Now, so consider the surface phi xyz is equal to k. what does this look like locally to the point x naught, y naught, z naught? Okay, so we've got some scalar function. I'm actually going to define I'm just going to define a scalar function for this. Okay, I'm going to define a scalar function as the distance of a point from the origin. Okay, so that makes sense in 3 dimensions. Okay, so r is just going to be the x squared plus y squared plus z squared. Now let's imagine we've got the surface phi of x, y, z is equal to k. That's just the shell of a sphere. Now, if I'm on the shell of a sphere and I move from one place to another, a short distance, let's call that this distance n hat, or like n. No, let's just call it x. What I've seen earlier is, or let's call it delta x, is that grad phi dot this vector delta x is approximately the change in phi. But if we stay on the surface of the sphere, the phi is not changing, so this is 0. So what we have is that this little vector which keeps me on the surface, if I dot it with grad phi, it's equal to 0. So I'm just going to call this vector, let's call it v for the velocity. Yeah, because I know that, so this is saying that the velocities that keep me on the surface are ones which are perpendicular to this gradient vector. So in the case of distance from the origin, grad phi points in the direction of greatest change, so grad phi would point directly outwards. Okay, and you can see that if you were to actually do the partial derivatives, you would get a vector which was parallel just to the xi plus yz, yj plus zk. Now, geometrically, let's just treat grad phi as a constant vector at this point. Geometrically, how would we describe the set of vectors that are perpendicular to a given vector? So what is the locus of v such that v dot grad phi is equal to 0? And we can just treat grad phi like a sort of fixed vector. So if I've got a vector n, what is the locus of the set of vectors which is perpendicular to n? Not a So if I give you a vector in 3 dimensions, so here's my vector, the set of vectors which are perpendicular to it is just a plane. So what that means is that if you've got a surface defined by a scalar field of being constant, then locally that contour is just the plane that is perpendicular to the gradient vector which points in the direction in which phi would increase. Okay, and this sounds very, very complicated, but this is something which we're familiar with because we live on a big sphere. So when we look at the Earth around us, we don't see the curvature of the sphere. We see something which looks like a plane. And that plane is the plane which is perpendicular to the vector which points up. And the vector which points up is the vector in which our distance from the center of the Earth is increasing. So locally, this contour surface looks like a plane perpendicular to the gradient of phi. So the gradient of phi in the context of the Earth is up. And locally, the point where distances don't change from the center of the Earth is that flat plane perpendicular to up. Okay. This relationship that, oops. Sorry, everyone. My laptop battery ran dead, which is probably my laptop telling me that it's time to finish. I pretty much said everything which I wanted to say. Did anybody have any questions? Did anyone have any sort of emotions? Does anyone, yeah, sorry, chat. Is phi, okay, so very good question. Very, very good question. I'll just put this from the chat. So it says, the question says, if phi x, y, z is constant, why does grad phi not equal 0? What you've got to realize here is that the claim is not, grad phi would be 0 if phi x was constant within some ball, yeah, or within the whole of space. Okay, but what we're talking about here is in a function defined on two variables. We're talking about a line, a contour line on which phi is constant, or in 3 dimensions, a surface where phi is constant. If we take the contour lines example, you should think back to your GCSE geography. So if you've got contour lines, yeah, so 100 meters, 110 meters, 120 meters, 130 meters, 140 meters. The line in which the hill goes is the line your geography teacher would have told you is the line which cuts as many contour lines as possible. Okay, so what you've got here is this line which cuts as many contour lines as possible is going in the sort of greater slope. So this is in the direction of the gradient of phi, and its magnitude will be the rise over the run in this direction. But when we're talking about grad phi being constant, okay, it's not constant in space, it's just constant along this line. And the 2-dimensional version of what I was talking about earlier of a sort of line of where phi is constant being like a plane, in 2 dimensions, the contour line locally is a little bit like a line. And it's which line? It's the line that's perpendicular to the line which points up the slope. Okay, so imagine if you just go hill walking and you sort of follow a contour. At each point, you sort of feel like you're walking in a straight line. Now, that line actually just sort of bends round, but that little line that you're walking on, yeah, perpendicular to it, there's a slope, or it might be at the bottom of it might be at a, it might be at the bottom of a valley, but perpendicular to it, there's a slope, and that the line of greater slope is the line that grad phi lies. Point is the direction in which gradient of phi points in. This expression here, that the rate at which the elevation changes with time is the gradient dotted with the velocity, that's showing that if your velocity is, the direct, if you walk in these various different directions, your elevation will be increasing most when the velocity is perpendicular with the gradient. Your elevation won't be changing when it's perpendicular to the gradient. You'll be going downhill if you're going in the opposite direction. So that is encapsulated in this. That is encapsulated in this idea here. Now, something which lots of physicists sort of visualize as being a little bit like a hillside is a potential, a scalar field known as potential energy. Okay, and in that context, if you move in a direction where potential energy is changing, you're doing work against potential energy. And if you move in so one of the things which is spoken about in the sheet is the special case if grad phi, if a force field happened to be also the gradient field of some scalar quantity, and let's call it minus, then the force dotted with V is the work done. but then this relationship would be saying that the force dotted with V, which is the work done, is the negative of the rate of change in phi. So it's the loss of something. So that becomes the work done is equal to the loss in potential energy. Okay, and that's explained in the sheet, but I think this is slightly easier to understand. So this is saying that the rate in which your elevation changes depends on the extent to which your velocity is in the same or different direction to the line of steepest slope. Okay, and as I said at the outset, really don't worry if you didn't fully understand those vector field parts of the question. That's something which we'll see a lot at university. The purpose of that part of the sheet, the part of this course is to sort of whet your appetite. Okay, any final questions, or should we let my laptop's decision to end this meeting win and change at this point? Will we be doing more vector calculus during COMPOS? Vlad, do you know the answer to that question? I'm not sure if Vlad's there. Would you like to do more vector calculus? Yes. Oh, brilliant. Great. Well, I hope there is. Yeah. If there is, then you will really like it. What you will see when you get to university is lots of the things that you've kind of been taught in physics really need vector calculus to understand them properly. So all the left-hand rules, right-hand rules that you see in electromagnetism, Maxwell's equations, exactly. Maxwell's equations will involve operators from vector calculus. And there's two, we've spoken a little bit about the gradient. There's two others called the divergence and the curl. Right, I think I need to go. I hope you've enjoyed tonight's session. I hope it's done two jobs, helped with some of the sort of questions that you'll see on the sheet, but also hopefully just explained a little bit of the vector calculus geometry. So I hope you've had fun. Okay, thank you everybody. I've enjoyed it, and oh, I'm getting lots of thank yous. Brilliant. Great. I will see you in a fortnight's time. Okay, bye-bye everybody.